Hello all, welcome to the video presentation for the course Artificial Intelligence Foundations and Applications for the autumn semester 2021. We are a group of 4 undergraduate students from the Department of Electronics and Electrical Communications Engineering. Our team consists of D. Pradyun, Devjit Chakraborty, Shivansh Shetty and myself Nivedita Maji. We have done our research and studies on non-intrusive load monitoring and will be presenting our findings and ideas in this presentation. So, what is RPS? The rapid urbanization of developing countries, coupled with explosion in construction of high-rising buildings and the high power usage in them, calls for conservation and efficient energy program. Such a program requires monitoring of end-use appliances, energy consumption in real time. The worldwide recent adoption of smart meter in smart grid has led to the rise of non-intrusive load monitoring, which enables estimation of appliance-specific power consumption from buildings' aggregate power consumption reading. NILM provides households with cost-effective real-time monitoring of end-use appliances to help them understand their consumption pattern and become part and parcel of energy conservation strategy. Now, NILM is the computational technique that uses aggregate power data monitored from single point source such as smart meter to infer the end appliances running in the building and estimate their respective power consumption. It provides households with cost-effective real-time monitoring of end-use appliances that facilitate energy conservation actions. Also, NILM system can help policymakers evaluate the effectiveness of their energy efficiency policies, while utility can better forecast demand and enable manufacturers to optimize product design to meet customer need. Several approaches have been proposed from the problem ever since its advent in the 1990s. And in this report, we try to find and investigate those AI mappings which prove to be the most promising. A computationally tractable and efficient solution will ensure effective and efficient energy saving in residential buildings through real-time monitoring of end-use appliances consumption and provision of real-time actionable feedback to households that give insight into what appliances and when they are used, how much power they consume and why such consumption. So what is our AI mapping? This problem can be modeled as Markov decision process. After sampling the power values obtained post cleaning the meter values, one can see the sequence either as a Markov decision process or a recurrent network. It is a search algorithm that looks for the user energy template for each device from the energy usage sampled from the electric meter. It applies feature engineering and ML and probabilistic models to generate the on or off timeline and report back unusual activity to the user. The motivation lies as such. The global need for energy is increasing rapidly and the demand for electric energy is increasing even faster. Between 2010 and 2050, electric energy consumption is predicted to double. Current power production methods, however, are not sustainable as the global population continues to expand and fossil resources become increasingly exhausted. According to the International Electrotechnical Commission (IEC), the most significant component in overcoming energy challenges will be the intelligent and cost-effective use of electricity as the principal energy source. As a result, studies are being undertaken on how to use energy more efficiently in workplaces, buildings, and households. As smart grid technology improves, it will be able to efficiently monitor and manage energy in houses. One way to improve the efficiency of home energy use is to encourage consumers to make positive behavioral changes. This can be accomplished by looking at how much energy is used. One option is to use non-intrusive load monitoring. Now, what is NILM? NILM, that is non-intrusive load monitoring, is a process aiming to identify the individual contribution of appliances in the aggregate electricity load. It is a process for analyzing changes in the voltage and current going into a house and deducing which appliances are being used in the house along with their individual energy consumption. NILM provides consumers with cost-effective real-time monitoring of end-use appliances, allowing them to better understand their consumption patterns and participate in energy-saving efforts. Now over to Shivansh.
Let's move to why NIM is important. The electrical usage profile of a user is, as Nivedita explained, is being returned by this algorithm. This algorithm monitors the end-use applicant's consumption and provision of real-time actionable feedback to households. These insights give users about what applicants are being used and how much power they consume and why such consumption results in effective and efficient in residential buildings. Energy consumption awareness combined with real-time actionable feedback to households inspires positive behavioral changes and engages households in pursuit of sustainable energy consumption. As a result, homes will be actively involved in determining where energy is wasted so that they can save that energy and thus encourage energy conservation behavior. However, deploying a sensing infrastructure is very expensive. It is inconvenient and necessitates the use of communication protocols. This has reignited interest in development of effective non-intuitive load monitoring, that is NILM techniques. NILM, along with policymakers, can also help improve the energy efficiency policies and generate better forecast that can be used by manufacturers in optimizing product design. Let's move now to the next slide to see how we achieve that specific goal. So energy disaggregation is a technique that estimates the energy consumed by every individual appliance in the house from a single energy measurement device like a smart meter. This technique is gaining popularity due to large-scale smart meter deployment worldwide. As you can see in this slide, we calculated every time step the power that is being consumed as a function of power being used by different appliances. These can be used in a 5-step process that starts from power being accused to the final inference in which we try to obtain the final result. This can be seen in the image on the right. At the first step, we take the data from those meters. Then we pre-process that data, try to identify several edges within that data, extract the features from those to identify which appliance is active at a specific time. We apply classification and regression techniques within that and try to find this aggregation technique that we are looking in this. Next slide, please. So the next process that we are looking for is this. We have a time frame in which we have the power consumption at several times. And from that, we're trying to apply NILM algorithm to find at specific different time locations. What are the appliances that are working and what is the power being consumed by those specific appliances? As you can see in the figure as well. We can start with which refrigerator or oven element, that is which of the appliances was active at which specific domain and at which specific domains is went down so that we can understand the duration it was active in and thus use that to identify the time duration and the energy being used by each specific design. Next slide, please. So as you know, this is a total 5-step process. The first step starts with power signal acquisition. In this, we entails connecting aggregated loads measurements as a sufficient role in order to identify discrete load patterns. As you can see in the image on the right, we first of all have a physical system that gives us the power. We try to identify several measurements, get an analog to digital conversion to obtain at several different points what are the values of the power to do samplings at different rates. The sampling frequency is determined by the measurements and electrical characteristics that our NILM algorithm is using. A cost-efficient approach for acquiring this is to use smart meters, which are currently being deployed. They generate these characteristics directly that can be used to give user more informed information that can result in better techniques. Next slide, please. So based on the data that we have, the second step that comes in is identification of several edge that can help us identify the appliance operation status that could be on and off from the power measurement. Changes in power levels, as you can see in the image on the right down. Once a device is on and off, we could see it by an edge. It is a complex process because of different types of appliances being on and off at different times. So we try to map these edges to several appliances. This could be done in two ways. The first is an event-based approach in which we try to identify the transition at a specific point with turning it as an event if the jump is higher. The second is a state-based approach in which we mark each point at a specific state and we try to map instead of an appliance a state to another state using state transition techniques. Next slide, please. So after this point, we have identified the several elements that has been occurring to identify the events that has happened. These events map us to a specific change in power that can be linked to a specific appliance. Now from these, we try to extract the features that can be used in terms of training the NILM algorithm. So we require unique features or signatures that can characterize an appliance and its behavior.
We try to do it via two methods. The first is a transient signature, in which how an algorithm is working within its settling time is being seen. As you can see image on the right in the red, and in the blue, we can see the settling time data. And in these figures, in which the algorithm is still is their transition behavior. However, after the transition behavior, it takes a finite value that it stays in its steady state features, as you can see in the green on the right. So we try to apply this on the data that we have generated to obtain the transition steady feature for each appliance. This can help us generate the unique energy consumption pattern for a user and for a specific appliance, and help can recognize them from the load measurements that we have. As you can see in the left image as well, from the data that we have, we can map different points as either an on event, off event, or a transient event, and we can map these data to obtain the figure on the right. Next slide, please. So based on this, now we have obtained the features that can be used to train a model. We'll discuss ahead several models that can be used on the specific data to obtain the results that can help us infer the happenings within the model. So in this stage, the extracted signatures that we have in the previous step are set to a specific model that is help identification of a specific state and estimates in power consumption. As you can see on the right, for a specific duration and a date, we have what are the appliances that were open, at what time were they open, and when they went closed. That is the feature map that we are looking for, which can be set back to the user, which on feedback can help sustainable energy saving to that specific user. So this information could help user identify where are the positions in which unnecessary consumption of power is happening, what are the inefficient appliances that are being used, and it also suggests optimizations, as we'll discuss ahead, and raise alerts, and thus make the consumer more aware of the energy they are consuming. This awareness can help reduce the energy that we are using, which we'll discuss ahead. Now over to Debajit to continue.
Now we will look at some artificial intelligence methods used to solve this NILM problem. Next slide, please. Recently, some of the most contemporary works in NILM is probably focused in primarily three broad fields of work. First of them would be hidden Markov models, where the states are directly not observed and each state is characterized by a probability distribution. The second, we use the graph signal processing method, which is basically an emerging field which is not fully explored, and it is trying to extend the classical signal processing theory to NILM problem. Finally, we will explore the hugely successful deep learning method, which has drawn heavily from the knowledge of ANNs, which is the artificial neural networks, which is basically modeled on the diagram of the brain. Next slide. So first of all, we will explore this hidden Markov models. Basically, in hidden Markov models, there are two variables, the observed variables and the hidden variables. In the context of NILM, the hidden variables are used to model the on-off states and etc. of individual appliances, and observed variables are used to model the electric usage. The mathematical modeling of HSM is as follows. The finite state is described via an array of states. The observed symbols is basically the outside observed symbols and not the underlying state. The transition function is modeled as an MTP, where each of the we get a matrix from all the actions with all the actions. The emission matrix is a characteristic of the HHM, which basically tries to show what is the probability at a particular time step. The initial state probability is also given as follows. The final representation is basically a tuple of the emission matrix and the transition function, as well as the initial state probability. Next slide. Before tackling this problem, how to solve the HHM, we should try to understand two important problems. First of all, given the sequence of observed values, since we are not getting the underlying state, how will we learn the model parameter lambda? And even if we learn the model parameter lambda, how will the sequence of observable states will help us infer the optimal sequences of the hidden state? Basically, to take an analogy, suppose you have all the data about the what is the cloth a type of person is wearing, but from the data you need to understand what was the sequence of the weather from last month to this month. So we need to infer that data. So those problems has been known as learning and inference problems, and some algorithms such as Viterbi algorithm and Baum-Wilch algorithm has been used to solve these. Next slide. So also an extension of HMM is built, which is known as a factorial HMM, which is basically used with multiple independent hidden state sequences, and each observation is dependent upon multiple hidden variables. FHHM are preferred to HHM for modeling time series generated by the interaction of several independent processes. However, the computation complexity of both learning and inference is greater for FHM compared to HMM. In addition, the inference techniques for HMM based approach is highly susceptible to local optima. So basically, in the down part of the slide, we can see how the mathematical modeling of FHM is given. Next slide. Some of the case studies based on HMM has been presented below. It has been used for energy disaggregation at low sampling rates. In one such case, we are using the energy disaggregation using a combination of 4 HMM variants. The authors use low frequency layer power feature and assume a binary state of appliances. Secondly, Kim approach uses MLE estimates to infer the load states. Some also use Bayesian networks for disaggregation of active power. And also, for the inference, the authors use the extension of Viterbi algorithm, which we mentioned earlier. Also, even a fully unsupervised NLM framework has been used using a low frequency real power feature. Next slide. Now we explore this field of deep learning where recently different type of structures has been proposed and they are hugely successful and we will explore them later. These are the recurrent neural networks, convolution neural networks, autoencoder, GRUs and all HMMs. However, some of the problems which has been faced is the lack of benchmarking data, lack of benchmarking in the field despite having a lot of data. Even our Indian power grid also provide the daily data, but there hasn't been huge amount of work in the benchmarking. To address this, some of the authors have come up with a very popular toolkit known as NILM-TK. And basically, right now, work is going on in this field for giving better benchmarks. Next slide. Some of the case studies based on deep learning are here. Some propose neural network ensembles to approach the NILM problem because the RNNs capture the sequence information, the CNNs acquire the objectal information. So an ensemble of them will provide a whole comprehensive information. The work by Kelly has been adapted to use three neural net architectures to low frequency energy disaggregation problem. In a parallel work, the authors also present a comparison of various CNN and RNN techniques for the energy disaggregation problem. Some of you may think why we are using low sampling. This is because of the fact that these models take a huge time to train, and if we are taking high frequency data, then we will have a lot of data which will make it computation intractable. One parallel work which proposes sequence to point learning with CNN is a single midpoint of a appliance window is treated as a classification output. Another interesting work proposes the novel combination of HMM with DNNs for load disaggregation, despite the fact that these actually outperform the HFHMM despite being trained on fewer data. Now we will move on to Pradyun, who will explain the various frameworks.
Thank you, Devjit. So, as Devjit said, there are several deep learning frameworks that can be used for classifying the NILM task. These include RNN, LSTM regression model, and CNN. So now let's go through RNN and LSTM regression model to understand how they actually work. In a recurrent neural network, which is RNN, we assume that we categorize the type of events that occur at each moment in a movie. So it's unclear how a typical neural network could use prior events in the movie to inform subsequent ones. This problem is addressed by recurrent neural networks. They are networks with loops in them that allow data to endure. So in the diagram, as you can see, a chunk of neural network A looks at some input text xt and outputs a value ht. A loop allows information to be passed from one step of the network to the next. A recurrent neural network, as shown, is made up of several copies of the same network, each of which sends a message to its successor and intricately tied sequences and lists as seen by their chain-like character. They are the most natural neural network architecture to employ for such data. Next slide. So what is the disadvantage of RNN? The recurrent neural network does not learn the order dependence in sequence predictions. So here comes the necessity of sequence predictions leads to usage of long short-term memory model, which is LSTM regression model. LSTM networks are a sort of recurrent neural networks that may learn order dependence in sequence prediction challenges. When there are more than 5 to 10 discrete time steps between relevant input events and target signals, RNNs fail to train. The vanishing error problem raises doubts about whether typical RNNs can truly outperform time window based feed forward networks in terms of practical benefits. An LSTM network is made up of memory blocks, which are recurrently connected blocks. LSTM can delete or add information to a cell state, which is carefully controlled by structures called gates. So we use three gates to decide how much information to let flow and how much to stop. LSTMs also have chain-like structures, but the repeating module have different structure. Instead of having a single neural network layer, there are four interacting in a special way. Now, gates are a way to optionally let information through. They are composed out of a sigmoid neural net layer and a pointwise multiplication operation. Sigmoid layer lets through when a value is 1 and a sigmoid layer lets nothing through when the value is 0. Now, initial step in our gate is forgetting. As you can see in the diagram, this step involves throwing out the cell out of the cell state, which we don't require in a modeling. Now, once we've thrown out the unnecessary cell, we come to the input gate. The input gate decides which value will update, and that would pass through the sigmoid function, which I've earlier said, and which will allow it inside. Now, the output gate will decide what cell state we're going to output. There is another other state here, which is the upper part of the block, which you can see in which the value gets updated. So these are the functions of gate and three different types of gates we use in LSTM. Next slide, please. So now coming to the results. These models and networks help us obtain pattern in the user's energy profile. As you can see in the diagram above, we can see the unusual usage of a refrigerator, the usual use of a refrigerator, the timestamps between which it is being used, and the aggregated power in watts which is also being consumed. In reporting any of the values, we observed energy consumption awareness combined with real-time actionable feedback to household inspires positive behavioral change and engages household in the pursuit of sustainable energy consumption. As you can see in the diagram below, the aggregated power of microwave and refrigerator are also shown. Next slide, please. So, to conclude, there are several NILM techniques for reducing or controlling energy consumption in residential buildings which have been proposed. Despite significant advances in the NILM field, energy disaggregation is far from solved. When it comes to real-time disaggregation that is general enough to be deployed in any household, the state-of-the-art algorithms still pose a number of challenges. So as we know, in a day and age where fossil fuels are getting exhausted and cities are consuming huge amount of power, we know how much we require to kind of use power in a sustainable manner. So the standardization of NILM performance metrics, the creation of efficient NILM benchmarking framework, and the availability of high quality energy datasets are all critical for energy advancement and the advancement of energy disaggregation research. So this our project also lays a benchmark for all the future researchers and developers to kind of work on new NILM performance metrics. Thank you.